Hello, good evening, everybody. Welcome back into the planetarium. My name is Kate Barnard. I'm the Programs Manager here at Scienceworks. Before we begin this conversation, I would like to acknowledge the Bunwurrung and the Wurundjeri people, the traditional owners of the land that we're gathered on. Indigenous Australians were the first astronomers in this country and have been looking up at the skies and doing science and astronomy for 65,000 plus years. So it's appropriate that we acknowledge them tonight. I would like to also let you know that we're totally thrilled to have sold out this event. Thank you so much for your interest in coming on the night before a public holiday. We would love to know what you thought of the event. In exchange for your thoughts, we have a small treat for you on the way out if you fill out a survey. So it's very short. It's really, really short. So if you fill out a survey at the end, you get a small treat on the way out. Thank you for your patience. We are running a little bit behind, but there's just so much to talk about. And I also would like to acknowledge that we're incredibly grateful to the US Consulate here in Melbourne for their support of the event. And it's an honour to host Deputy Consular Chief Michael Mitchell here. And in a moment, I'll invite him up to the stage to give some opening remarks. Now, when Alice and Sarah are up here on the stage, I would invite you to lean back if you like so that you can see the PowerPoint up on the screen, but whatever is most comfortable for you. All right, can I introduce Deputy Consular Chief Michael Mitchell.
Thank you. So thank you very much. On behalf of the Consulate, I'm very pleased to be with you tonight here at Scienceworks. Our governments have spent a lot of time this year talking about space, whether it's the 50th anniversary of the moon landing or the opening of the Australian Space Agency. It's clear that space exploration captures the imagination in a way that very few topics do, whether it's nostalgia for the past or excitement for the future. It's also clear that along the way, the United States and Australia have been hand in hand on this thrilling journey, whether it's the critical role of the Honeysuckle Creek tracking station that played a role in allowing 600 million people to watch the moon landing in 1969, or more recent history that we'll explore tonight. As NASA's New Horizons spacecraft approached Pluto and its 5 moons a few years ago, it was the Canberra Deep Space Network that carried all the data, the imagery, and Pluto's atmospheric measurements. In August this year, the Mars 2020 and ExoMars rover science teams honed their skills in the Australian outback, where the rocks are of similar age to the terrains on Mars. And this was in preparation for their missions to launch to the Red Planet next year in search of signs of past life on Mars. And in September, Prime Minister Morrison announced that Australia will join our Moon to Mars exploration approach, including NASA's Artemis lunar program. Through Artemis, NASA will send the first woman and next man to the surface of the moon by 2024 and establish sustainable exploration with our commercial and international partners by 2028. NASA's Artemis program is the next step in human exploration and is a part of America's broader Moon to Mars exploration approach. It's the honor of the US Consulate to help bring you these 2 American superstars tonight, Emmy Award-winning journalist Sara James and NASA New Horizons Mission Operations Manager Alice Bowman, to talk about NASA's New Horizons spacecraft and its audacious journey to Pluto. Please make them feel welcome, and thank you once again.
Good evening, everyone. My name is Sara James, and it's my pleasure to be here with Alice Bowman. It's my pleasure for a couple of reasons. First of all, who here is as excited as I am to hear from the Mission Operations Manager herself? So in addition to that, which is really quite magnificent, I have an extra little secret, which is that I have the great pleasure of having known Alice for quite a long time now. Alice and I are both from Richmond, Virginia. I now live here in Australia and am a dual citizen. But Alice and I went to the same high school and the same university. So it is really a thrill to get a chance to be here to talk to my high school and college pal. And there's another aspect to that, which is that since we went to school together, we had the same textbooks.
We did.
And Pluto didn't look like the Pluto today.
Not in any sense of the word.
So what did we know about Pluto back when you and I were in high school, and why did we have to go there to find out a little bit more?
Well, when we were in high school, we knew about the sun, Mercury, Venus, Earth, Mars,
We knew about the
Jupiter.
dinosaurs. No, I'm just
Yeah. And Pluto, we knew it was out there, but the only thing that our textbooks told us was that it was a small gray rock. At least that's what mine said, and I guess Sarah's as well. And since that time, we've learned a lot more. Even before we got to Pluto, we learned of this other region called the Kuiper Belt, which actually starts beyond Neptune and goes out beyond Pluto. And so one thing that we have here, we have the distance between the sun and the Earth, which is 1 astronomical unit, or 1 AU, which is 150 million kilometers. So kind of keep that in mind when we go through this. And it takes a photon from the sun 8 minutes to travel that distance to Earth. So that photon that you're seeing, the sun coming in, is 8 minutes old by the time it reaches here. So this Kuiper Belt is this donut-shaped region, and if you were here at the earlier presentation, you saw that. It's this donut-shaped region composed of these very small particles, and also things like Pluto and Eris and Makemake. And on the screen you can see this yellow circle, that is the path that Pluto follows when it goes around the sun.
And it takes a long time to go around the sun.
It does. Pluto takes 248 years to go around the sun, and it was closest to the sun in 1989. And so when you're closest to the sun, that means you're warmer, and ever since 1989, it's been coming back to the longer part of its orbit, so it's going away from the sun, away from the Earth. And we wanted to get to Pluto as soon as possible because our scientists knew it had an atmosphere, and we knew that as it got colder, there was a chance that the atmosphere was going to freeze to the surface of Pluto. And we didn't want that to happen before we got there because we wanted to study that atmosphere.
But it was going to be really daunting because the challenge of getting to Pluto, I mean, we're talking about something that is far. You were in on the ground floor. You were in on the design phase of the Pluto mission. So what were you doing as you figured out how are we going to get from Earth that far in space?
Yeah, so our mission designers designed this path that we were going to use Jupiter as a gravity assist to get there in a shorter amount of time. It actually shortened our transit time by about 3 years. But the other thing was that we had to build this spacecraft that was very efficient in power use. It was a nuclear power generator that we used on the spacecraft to give it power. And by the time we got there, we knew that power would be a little over 200 watts of power. And if you know how that is, if you ever use light bulbs,
Yes.
there was about 3 60-watt bulbs that spacecraft could power. So we had to build those instruments on the spacecraft to be very power efficient. And this encounter with Pluto was going to happen very far away from Earth. So there was no way that we could save the spacecraft from a command from Earth. So that spacecraft had to really take care of itself. And we had to build that spacecraft to be very robust because it was going to be 9.5 years before we actually got there.
So the technical challenges of this mission and the distance that Pluto is, I mean, can you remind everybody how far Pluto is?
When we encountered Pluto, it was 32 AU from Earth. So 32 times 150 million kilometers.
That's how far
That's
you
how
had
far,
to get.
Yeah, and so that comes out to be about 5 billion kilometers from Earth. And remember we talked about that photon. It takes 8 minutes to go 1 AU. So if we communicate with the spacecraft using light waves. And so when we send information to the spacecraft, it's going to take 8 minutes times the 32 AU And if you do the math, work it all out, it comes out to a little less than 4.5 hours for us to get a command from Earth to the spacecraft. So really long time. And that's not difficult enough. This is a flyby mission. You only have one chance to get it right. You can't go back and do it over if you miss something.
So, I mean, if you were here for how many of you were here for the earlier planetary? Yeah, so pretty much most of you were here for that. So when you look at it retrospectively, it looks like, oh yeah, that's very straightforward. That's NASA doing their job. But the reality is, when you're trying to build and create this, and again, you were in on the design of this, you are having to figure out, how are we going to create a spacecraft that can do everything that we want?
Yeah.
What did it take to get NASA to agree to this and to create a spacecraft that could do it?
Yeah, so it was a lot of hard work, a lot of teamwork, we had a number of different companies that we partnered with, and we all put forth our best proposals for these instruments. And when you look at this list of instruments, or we call them payloads, there's 7 of them, and we have visible imagery going on. We have ultraviolet, we have spectrometers, we have dust counters. We're trying to cover the whole gamut of scientific instruments that could tell us a lot about Pluto. And we built the spacecraft to be very small. And the reason, small and lightweight. And the reason why we did that is because we wanted to put it on the biggest rocket that we could afford. And if you have a big rocket and a small spacecraft, that means that most of that energy of the rocket you can leave Earth really fast and get to Pluto as soon as possible. So we wanted to get there again before that atmosphere froze to the surface of the planet. And 50,000 kilometers per hour is about what we left Earth at. So we're still the fastest man-made object to have left Earth. So.
That's amazing. I didn't know that, as much as I know about this mission. Now, when we talk about this mission, we need to explain to people who you are, because you have a very special title. You're Mom.
I am Mom. And all NASA missions have a mission operations manager, and even if you're a guy, your call sign on the radio is Mom. And so what we do is we manage the operations team. We take care of the spacecraft. We're looking at the telemetry or data coming in from the spacecraft. We're making sure that all of the temperatures and the voltages are within the range. We're also working with the scientists and the engineers to understand what they want that spacecraft to do, and we're building the commands or the set of instructions for the spacecraft, and we're testing them on the ground, making sure they're going to do what the scientists and engineers want them to do. And once we've done that, then we are going to send that information to the spacecraft. We configure the ground station to make sure that it matches what the spacecraft is expecting. And then we bring that data down. And then, if something isn't quite right on the spacecraft, we're the team that leads that effort to recover.
And that will become very important a little bit later in our tale. But one thing to mention is the fact that, as I discovered a few years ago when I was with you, this pretty place, who knows where this is? Call it out if you do. Yes, it's in Canberra. So that is crucial, isn't it, to this mission?
It is very crucial. And
I'm going to pass this, Alice and I are going to pass this back and forth. But tell us about the DSN, the Deep Space Network, and Canberra's role.
So the Deep Space Network is composed of 3 complexes around the world, and they're basically separated by about 120 degrees. So when you add that all up, that's the 360. And the first one that we're going to talk about is in Madrid, Spain, and then Goldstone, California, and then, of course, here in your country, Canberra, Australia. And these stations play a crucial part in all space exploration. And for us, for the New Horizons mission, Canberra Station, remember you saw that picture of the yellow path that Pluto traverses when it goes around the sun? It's kind of tilted, mostly towards the southern hemisphere. And so for us, for our spacecraft, we get the largest period of time with Canberra Station, more than any other complex of the Deep Space Network. So it's really important.
And I know you
was.
have some slides here where you can show us about how you do your communication
Yes.
with the data. So we talked about the distance, the time that it takes to communicate between Earth and the spacecraft. Can you explain a little bit more about that?
Sure. So we load the instructions to the spacecraft. We load about 2-week chunks of time. We load it to onboard memory. So we send that up to the spacecraft. There's a clock on board the spacecraft, and each of those instructions or commands is tagged with a certain time to execute. And so as that clock ticks down, those commands execute out of memory. And so what we're showing here is if we want to bring data down from the spacecraft, then our onboard instructions start sending that telemetry down, let's say at time 0. But at the bottom here, you can see that the station on the ground could be supporting another mission. And the example here is, I got this backwards. The example here is when the spacecraft's at Pluto. So we're 32 AU from Earth, and we start sending that telemetry down. But this station down here can be supporting another mission, another NASA mission or ESA mission. And as the data comes down, now we're about halfway down, 2 hours and 12 minutes. But look at that spacecraft. Look how it's moved across the sky. And then finally, a little less than 4.5 hours later, that bit of telemetry finally makes it to that ground station. But look at where that spacecraft has moved. 231,000 kilometers across the sky. Likewise, when we want to send something to the spacecraft, we actually point that ground antenna to where the spacecraft's going to be a one-way light time later, or a little more than 4.5 hours later. And so, oops. Am I clicking? And so it starts moving across, and then the spacecraft.
Do you want to click it?
It won't go.
Oh.
We're stuck.
There it is. There it is,
Okay.
receiving commands.
And so finally, that spacecraft is there to catch those commands coming from Earth.
So basically, you have to aim at a place where you have to get right where it's going to be.
Exactly. So you're getting data from the past, and you're sending to the future. And,
Every single time.
every single time. Yep.
So the logistics of this, you're getting a sense of how complicated this mission is. So when you do this, you are doing this over a fair degree of time. Months pass, years pass, and that I loved how you pointed out earlier that NASA has a lot of patience. And it's true. There is a lot of patience, there is a lot of time. But then, as we'll show on our next slide, we get to a stage where it all starts to happen. So
Yeah.
after, and it's funny, I will call Alice periodically to catch up with her, and we'll talk about the differences between our industries. Because when I'm talking in journalism about a deadline, I'm thinking about something that's minutes away. And your deadlines sometimes are a year away, and you're in very serious planning mode.
We are. We actually started planning this 9-day flyby sequence in 2008, but we didn't get to Pluto until 2015. So that's what you do when you only have one chance to get it right. And the gentleman, Owen, spoke before about this discovery of the moons. When we launched the spacecraft, we knew there was the big moon Charon, and then the two smaller moons, Nix and Hydra. And then along the way, Kerberos and what was the other one? Styx,
Charon?
Nix,
No.
Kerberos and Styx were discovered. And it caused us to rethink how we were planning that 9-day flyby sequence. And we actually developed another set of commands that we could put up if we found something that was dangerous for the spacecraft.
So when you did this was a complicated thing because you've already told us that you have to program for the future, but you had all of this information that you were going to need to get, didn't you? So you needed to, I guess, send some pretty complicated instructions to the spacecraft to get the information. So tell me about, if you can, what happened on July 4th, 2015. What's the significance of this, other than being U.S. Independence Day?
Right.
But on this particular U.S.
Yeah.
Independence Day, it's a lot more significant for you?
So this was the very first day that we actually had the memory free on board the spacecraft to accept this 9-day set of commands that would accomplish the flyby, all the scientific observations, because we could not load it before then. And so we started loading this set of commands, so we call it radiating or uplinking this set of commands, and it took 2 hours to radiate or send these commands out from Earth. And we were actually using the station at Goldstone, the 70-meter station, to send these commands. And then a round-trip light time later, so a one-way light time up to the spacecraft, and then another one-way light time down to Earth to receive the telemetry that would tell us if these commands had been received correctly. So we were watching in the operations center, and we watched the main computer on board that spacecraft receive these commands. Everything was going perfect.
So everything looked great.
It did. Until
that moment.
Yeah, 1:54 p.m. Eastern Time.
And what happened? What did you see?
Nothing. We lost communications.
So to put this in perspective, you've been years getting there. You're 9 days out of the biggest opportunity that you're going to have with a one chance to do this. What went through your mind at that moment?
Well, I won't quite say the word, but
It's Australia, you can say.
yeah. Okay,
but
so you get the point. Yeah, it was like, oh my God, can this really be happening? We'd flown across the solar system pretty much with, people paid attention to our mission when we launched, and maybe when the pictures came back from Jupiter, but then we pretty much flew quietly across this great expanse, and then all of a sudden we had all this media attention because we were going to be the first to see what Pluto looks like. And we had a whole bunch of media on campus. And for me personally, I allowed myself that, 10, 20 seconds, like, oh my God, I can't believe I'm doing this, and you're figuring out what the heck. And then all your training kicks in. You've got a mission to lead. There's no way that we were going to let this opportunity get away from us. We were not going to let ourselves down, the team down, the world down, really, because everybody just seemed to be interested in the mission.
And so when you got to that moment, who was on deck? Which part of the DSN at that moment was on the line?
Can you guys guess? Yeah, Canberra was up with us. So we were up with the 70-meter at Canberra, Station 43, and they were fantastic. They take instructions from our operations center, our flight controllers, or we call them Pluto aces, and we were trying to figure out what could be happening. And one of the most likely theories was that we had experienced a main computer fault, and that we had switched over to the backup computer. And so that the software on board that would do that takes a certain amount of time to switch over. And the other credible faults were a little bit distant. We weren't quite at that point. So we asked our Pluto aces to ask the DSN station, Canberra station, to reconfigure the spacecraft to receive a signal if we were in that sort of anomalous or abnormal condition. And 77 minutes after we lost communication with the spacecraft, we locked up to signal. Hooray. Thank God we got it. But
there were still problems.
There was. We were in what we call a safe state, which means that we could not take any pictures of the Pluto system. We were in a spinning state. And again, this is the afternoon of July 4th. And our 9-day...
A holiday, by the way, in the United States. Yeah. Not that anybody would have been marking it at that stage.
Yeah. And our 9 days, this flyby sequence or set of commands was to start on July 7th. So that gives you an idea. And the distance. Remember how far away. it's
So
gonna
at
take.
that stage, you really had to make a couple of decisions, didn't you, in terms of
did.
what was absolutely necessary? Can you tell me about the conversations, what went into the conversations about what you were going to do now?
Sure. One of the things that we worked as obviously a team, and many of our team members have been with us since the start of this mission. So we know each other well, we know our process well. We'd been through anomalous conditions or abnormal conditions before, but nothing as high stake as this. And so one of the first things that we do is we hold a meeting. We call it the anomaly resolution meeting, and the operations team comes in and we give all the information to the engineers and our management that we have at the time. And thankfully, we had locked up 77 minutes later, and so we knew the state of the spacecraft. We had a good theory of what had happened. And, we say this, we go around the room and we have anybody that wants us to get more data from the spacecraft or has any questions. And the last gentleman to speak was our principal investigator, Alan Stern. And he looked at me and he said, "Alice, what do you need?" And that was quite daunting at the time.
What did you say?
And I said, "I need you to tell me where we need to pick up the set of commands. Where do we need to recover the spacecraft? Do we need to go back and recover what has happened on July? It was going to happen on July 5th or 6th or what?" And he said, "Save the cake, forget the icing." And what that meant was that we had those 3 days to do whatever we needed to do to recover that spacecraft, but we needed to start that 9-day flyby sequence on July 7th.
So tell us what we're looking at here. We know that there's no second chances, but tell us what this means, the significance of this important slide.
So we did recover the spacecraft, and we had about 4 hours to spare on July 7th.
4 hours.
4 hours, yeah, because it takes so long to we send up a set of recovery commands, make sure that everything was good on the spacecraft, send up the next set, and we were able to start right on time. We're fast forwarding now to July 13th, and remember that the closest approach of Pluto was July 14th, 2015. So here we are at the very bottom of, at least on mine, it's the bottom of the screen. Okay, over here. Is this one? Yeah, here's the last contact we had with the spacecraft. Last communication, last chance to check that everything was normal before we went through through the Pluto system, taking this scientific data. Our spacecraft can't be in communication with Earth at the same time that it's taking science observations. So this period here is 22 hours where the spacecraft flew, taking scientific observations, using all of our instruments on board the spacecraft, but with no communication to Earth. So we did not know what was going on for 22 hours.
And also, let's point out that this is a really complicated time because it's the most scientifically important, but is it a free area? Is it free of risk?
Yeah, so we had been doing measurements on board the spacecraft and checking them on Earth and making sure there wasn't anything here. But, we were surprised once by the discovery of 2 new moons. Anything here on our path, the size of a grain of rice, could cause catastrophic damage because we're traveling so very fast, 50,000 kilometers per hour. And so it was very treacherous, and our opportunity to see if we had survived the transit through the system is going to come here on July 14th Eastern Time, a little bit before 9 o'clock p.m.
So do you want to have a look and flip to the slide that comes
Sure.
next?
So I want you to, this is what the spacecraft was doing in these 22 hours. Out of contact with the Earth, and it's going to go fast. It's sped up, so it's 20 seconds, the 22 hours represented by 20 seconds. And if you look at the top part, you can see which instrument on board the spacecraft is taking the observation, what the target is, And then you can see the distance. I'm sorry, these are in miles, sorry. The distance to the target. So you can see how very fast this spacecraft is moving and how agile it is. And you might say, well, why don't you have something gimbaled, or why don't you just point that individual instrument? Remember, we had to build this spacecraft to last a very long time. It's going to take us 9.5 years to go to our primary target. So we have to point the whole spacecraft in order to take these measurements.
And remember, there are no second chances.
Right, no second chances. So now here we are. We are going to establish communication with the spacecraft after it's gone through this observation period. And the next, what you're going to see is a video of the Mission Operations Center. You'll see all the engineers in the Operations Center. Behind the glass are our managers, and the agreement was that they could not come into the Mission Operations Center until we had determined that the spacecraft was healthy. And so you'll see this.
So let's have a look at what happens. Now remember, Alice doesn't know at this stage whether or not the spacecraft has survived. It's been 22 hours of silence. Let's have a look at what happens next.
And lock on symbols.
So that's the first step in getting data.
Okay, copy that. We're in lock with telemetry with the spacecraft. Lots of people in the Mission Operations Center, usually not this crowded. But this was a special day.
See a lot of green numbers in that book. Yeah, green is good. Yeah.
You're looking a bit relieved here.
Yeah. Definitely.
You gotta get that, man.
And this is the auditorium at Applied Physics Lab, so they were piping this in. This was also broadcast on the internet. Okay. PI, Mom on Pluto 1. We have a healthy spacecraft. We've recorded data of the Pluto system, and we're outbound for Pluto.
That's it.
Here's our principal investigator, Alan Stern.
But to be clear, you told Alan he had to stay on the other side of that glass until you knew. Is that right?
Yep.
And why was that, all joking aside? Because you needed that space, didn't you? I've been there. It's a really small little area. I don't quite get the sense of that.
Yeah, definitely. We needed to be able to do our job, and he was very respectful of that. So, we're a team, and we respect each other, and we know we all have the important things to do in our job. So this is what Pluto looked like before New Horizons. This is an image taken with the Hubble Space Telescope. And if you're not a scientist, you might look at that and say, I don't know. But if you're a scientist, you're going to say, wow, that's going to be really interesting.
How can you tell that? This is a bunch of squares.
Well, because there's a lot of contrast there. There's a bright area, there's kind of dark areas. Yeah, I know you're looking at it funny. But if you're a scientist, you're going to say, wow, that's going to be really neat. We got to go there. And
But when you say really neat,
did
you expect what you got?
No, not at all.
So I want to hand over the clicker for you to get to do the next thing.
Okay.
Let's see what you got.
So this is sort of a little recap of
Why
recap.
we go.
Why we go, when we launched, and then a composite of the things that we actually saw. So.
What's it like to look back at that?
It kind of brings tears to my eyes. It was quite an amazing journey, and what we saw was just beyond belief, really.
I think a big round of applause for the success of the Pluto mission. Well done. Thank you, ladies and gentlemen. I think you get a sense of all that went into the mission from seeing, there were real moments of consternation, and there's a lot of hard work that went into that.
Yeah,
So
every single
congratulations to
person,
everybody on the
yeah.
team for getting there.
Exactly.
So just as we move on, though, the spacecraft is still hurtling through space. So you've seen these enormous, I should just give you 1 minute of all the beautiful things that you saw on Pluto. There's the heart, there's the blue atmosphere, there are those volcanoes. What really touches you about what we saw from our textbook, where it was just a little dot, and to people downgrading Pluto as a dwarf planet, which we won't even go there, to what you saw when you actually had those beautiful images? What stands with you?
It's the reason why we're curious, why we go and explore, because what we can see with our eyes from Earth is not necessarily all that's there. We need to really go and see it. And if Pluto can hold all these wondrous things, can you imagine what else we can find out there? It's just astonishing to me.
And speaking of which, your
Yeah.
spacecraft was continuing to move even as you were getting those great images and downloading that data. It was traveling further in space. So certainly you had to be saying, now what?
Yeah.
So
Yeah.
tell me about this.
So spacecraft's still healthy. We, with the help of the Hubble Space Telescope, we were able to find 3 other objects that were within the realm of the propellant we had on board, left on board the spacecraft. And we chose another very small object called Ultima Thule to go and explore. And this is was about, 1.6 million kilometers. I'm having trouble with the math, sorry.
Well, and we're switching between kilometers and miles,
Yeah,
which
so
is
it's
also doubly daunting when you're
Yeah,
having
so
to
it's a
switch back and forth.
billion miles beyond Pluto, and so it's a little bit 1.5 billion kilometers beyond Pluto, I think.
So the fact of the matter as well is that it's not as big as Pluto. And remember, Pluto got downgraded. So we're talking about something really tiny.
Right, but we don't really know a lot about it. This object was discovered in 2014, so it's really new. Here we are, we're in 2015, and there's an object that's only been known for a year, and it's very, very small. So it's on the very edge of detection with the Hubble Space Telescope. And so we really need more information to accurately target that object. So if you have a gigantic object, relatively speaking, even if you're a little off in your pointing, you're gonna see it because it's larger. But if you have a small object, you have a good chance of missing it completely if you don't know where it is.
So the technical challenges are daunting. And then you have to figure out how to find something that small.
Yes.
So I want to give you an opportunity. I'm going to hand back over the clicker because the way you do this is
this is
quite
pretty cool.
remarkable.
It is. And again, this is a flyby mission, this other object, so again, one chance. And I just wanted to point out a couple of things here that we thought flying 12,500 trouble with I'm sorry kilometers from the surface of Pluto was daunting, but now we're going to fly much closer, almost 4 times as close to this very small object that we don't even know where it is. Pluto was discovered in 1930, so we had time to observe it. And so what the scientists wanted to do was like, oh my God, are you really? And we have a longer light time delay. So while it was about 4.5 hours to Pluto, we're at over 6 hours to Ultima Thule. So what our scientists did is they did the math and the calculations, and they said, okay, there are 3 opportunities where we could try to observe this object from Earth. You guys, everybody know like an eclipse. So an occultation is really an eclipse. It's when an object moves in front of another object. So in our case, an eclipse, you have the sun and the moon, or the Earth, would move in front of the sun, and it would occult the sun for a certain amount of time. And that depended on where you were on the Earth, right? So some places would see a total eclipse where the moon would completely block out the sun, and some people would see a partial where they would just blink out part of it. And so an occultation is like that. So we had 3 opportunities to get some more information on this object. We'll give you some information on exactly where it is and perhaps how big it is, and if we're lucky, maybe the shape of what we might expect. So the first opportunity was in June, and this one was in the path of that occultation was going to come across South Africa, a place in South Africa. And on July 10th, 2017, the second opportunity was actually going to be between off the coast of New Zealand, so in the middle of the Pacific Ocean. And we couldn't set up telescopes there, so the way they did that one is NASA has a plane called Sophia that has a telescope in it. And so the idea was to give these pilots a daunting challenge of being at a certain point, a certain time, and then open up those telescope covers and take observations. And then the third one was over Argentina, July 2017. Now, usually when I'm talking about this in the US, I ask my kids, well, what kind of weather, or what season is it in Argentina in July?
But we kind of know that.
You do, so that's an easy question for you guys. So,
but the fact of the matter is you went to no small amount of trouble in
Right.
Argentina, because this was really your last shot.
It was. So in June, the observation in South Africa, we didn't see anything. And so what that meant was we were off in the calculation of the path of where you could see it from Earth. Then we went back and they did more refined calculations, found a little error. July 10th, we only have one plane, one observation that we could make, and they think they saw something. But any kind of scientific observation, you really want to have more than just one measurement. You want it to, you want to take a good sample set.
So show us what you did in Argentina.
So in Argentina, this again was the last chance to get this right. So what we did is there was people sent down to Argentina with telescopes. Each one of these blue dots represents where a telescope was set up. There's 24 of these lines here, and they're manned by a 2-person team. We didn't send that many people down to Argentina. What we did is we had a core set, and then we invited scientists in Argentina to come participate with us to do these observations. And so the blue lines that you see are represent what we call the error bars. The yellow line is where the calculation is saying that object, the occultation, is going to occur. And then beyond those blue lines, we always set up, just in case we got it, not right, we want to see if we can see it with those. So again, each one of those green lines is where a telescope is set up, and we're on the coast of Argentina in the wintertime. It's very notorious for being windy and just kind of nasty.
It's actually never cold or rainy here, so we don't get that part of Argentina.
Okay. And so this little video here just shows you what they did.
Right.
So very desolate.
Handle time. Okay, within the next minute. And I will tell you if I see the star disappear. Oh, I saw it!
No way.
I saw it. I'm pretty sure I saw it.
Holy cow.
I actually saw it.
Holy cow.
No, I really did see it. a team, succeeded in getting not one, not two, but 5 different occultations. So we saw the star go out and come back as MU69 passed in front of the occultation star at 5 different locations.
So pretty exciting. So they got it on the 3rd try, and you saw how excited they were. Our colleague Amanda Zangari was the one that was doing the data analysis there.
So what did that show you? So now that you'd had that occultation, could you
Yeah,
tell what
so
you were looking
remember,
at out there?
We are looking at an object, however many we said, 6.6 billion kilometers away from Earth. And these lines here represent what the observations in South Africa. And so you can see those lines are unbroken, which means they did not see that star blink out. So we didn't see anything. And then here is the Sophia. We saw something, but again, only one sample, so we're not sure. So that's the blue line, July 10th. And then we had 24 telescopes set up. And this is where when he talked about the 5 telescopes that saw the occultation, this is where they were. And the length of the black period represents the time that that star was occulted or invisible, blinked out by that object. And so you can see here this middle one was the longest one here, but still only represents like on the order of less than a second. But still, now we found it. And
So
we
you
know
found it, and so if you look at it, who wants to guess what that is? Who can tell me what that is? What's that shape? What's it going to look like? It's a snowman. That's what I thought. Is it a snowman? Do we know it's a snowman?
We don't know
from that?
yet. We have some shape theories. So before we went, we had some theories about what it could look like, because it depends on which way you think you've caught it. But to a little fast forward here, this object is very small. So finally on December 30th, so just 3 days before our closest approach, which was January 1st, this is what came into the operations center. On the raw image is unprocessed, and then the processed one is the one that's called sharpened. So you can still see we don't know a lot about it, even on December 30th. And then the next day, now it's starting to take a little bit of shape.
Bowling ball. I mean, bowling pin.
Yeah, or peanut or
Peanut.
something. Yeah.
And look, by the way, ladies and gentlemen, notice how small it is. It's 33 kilometers, and it's 6.5 billion kilometers away. Just kind of take that in. Okay,
Yeah.
keep going.
So finally, January 1st, this is what was returned. Not a sharpened image, but definitely this is where you could say that perhaps...
Definitely a snowman.
Definitely a snowman with a big... Some people see eyes and a face up there at the front part where that crater is. And then the highest resolution image here. So it looks like 2 things put together, what the scientists call a contact binary. And, not being very imaginative, we're all very tired. We name one object Thule and one object Ultima, And so you might have been confused in the video. The real object's name classification is 2014 MU69. And we nicknamed it Ultima Thule, which means in the Vikings lore is the land beyond the unknown. And so that's why you hear both those things that we call it. So how many people think it's a snowman? You can raise your hand. Any other guesses? Any other guesses to what you might think? Yeah, so remember we talked about scientific observations. You want to have a couple of different observations to kind of collaborate and to make your theory, more than just a theory. So one of the things that we did, just like at Pluto, when we got past the object, we looked back and had the sun light the object. And this is what we saw. And the scientists, oh my goodness, that's not supposed to look like that if it's a round object. Because we would have expected that we would have had more of a glint here. This would have been larger here. And so all of a sudden, we're not looking at a snowman. We are actually, doesn't help with.
There
There
we
we go. Yes, thank you. So actually, what we're seeing is a flattened object. We're calling it a pancake, which is the bigger part, and the walnut, which is the Thule part. And so it's a really interesting object. We all kind of expect it to be roundish, but it's not. When you look at it from the other angle, it's kind of flattened out.
So that's why you have to do science, because it looks like a snowman, but it's not.
Yeah, so how did we do? So here's the data that we gathered from Earth, 6.6 billion kilometers away from Earth, this very small 33-kilometer object. So how did we do? Well, it fits right in there. To me, that is amazing that we can look into the sky with our telescopes and understand something this small, this far away. Amazing. And so if you think about the New Horizons mission, when we went to see this object, it's like a step back in time. We've made the most distant planetary flyby in history. And it is taking us back into the beginning of formation of the solar system. And one thing that these observations have done, there's always more than one theory about how the universe was created or any other thing. And so you have this hierarchical accretion model that some scientists use, and then we have this pebble cloud formation model. And I know that doesn't mean much to you guys, but there are these two theories about how the universe or the solar system formed. And what New Horizons has just done is actually led some more accreditation to the pebble cloud theory. And this has to do with how gently these two objects appear to have come together. There's no fractures there, so it was a more gentle combining, which kind of goes along with this pebble collapse theory.
So first of all, another round of applause for finding this tiny object. And as we get ready to wrap up, because I want to allow time for questions and answers, but as we go back for a moment to, so you found this tiny little object, you were able to get some pictures and flying by of that, but returning for a moment to Pluto, just to put that in perspective, when you set out from Earth with the notion of getting to Pluto, how many years was it from when you launched to when you got there?
9.5.
And how far was it roughly?
Kilometers?
4
billion kilometers.
4 billion kilometers.
4 or 5, yeah.
9.5 years.
9.5 years.
So according to your estimate of when you would get there and the distance, how close did you come?
To Pluto, yeah. We came in 88 seconds early, and we were 26 miles off the aim point from, 4.5 billion kilometers from Earth. And but I always say...
Could you have done any better?
Yes. I always say we could do better, but with that July 4th anomaly that we had, we were a little bit gun-shy. We were within that error box, and we decided we weren't going to make that correction.
Next time, you're just going to have to do better. I want to show, as we get ready to give you an opportunity to ask some of your questions, where next?
Yeah, so we are looking for another target. We have some propellant left in our tanks, but we are at about 44 AU from Earth, and the Kuiper Belt, we think the edge of it is around 50. So we're kind of running out of objects. We're hoping that we're going to find something. Hubble Space Telescope can't really help us anymore, so we're going to have to figure out a way to find a target using our own spacecraft, probably. And
You've done it once?
Yeah, we've done it. Well, yeah, we had help, a lot of help from Hubble. And so New Horizons, even if we don't have another flyby target, we will, we have a mission where we can go on and collect what we call in situ data, which is the Voyager spacecraft are still doing to this day, and we can return valuable science data. And so many times we get the question like, where is New Horizons in relation to the Voyager mission? So here you go. So we're sort of in the direction of Voyager 2. We're not quite as down in the ecliptic as Voyager 2 is. But we believe we can have a good mission out to the mid-2030s, even if we don't find another object.
Is Canberra still a key part of your mission?
Oh my goodness, yes. Canberra is still a huge part of our mission. We can't do it without them. And when we went to the station about 3 years ago, we're happy to take this middle picture here. I don't know if any of you know
Because
these
I
guys.
think probably everybody does like Australia and wears a Hawaiian shirt to work in the DSN. Is that right?
Yes.
Yeah,
perhaps.
I love that about us.
Yeah.
And as you look back on some of the greatest hits, who is this gray-haired guy who got a chance to meet you? You're so lucky. He's so lucky he got to meet you. Who wants to tell me who that is?
Yeah.
They're on to it.
So Brian May is part of our science team.
So of Queen, for those who don't know, there's a lot of people who do. Yes.
So he's part of our science team. He's an astrophysicist, and his specialty is looking for images where he can create a stereographic image. So, he was here, and this was taken. I think it was the 31st of December. He was in the Mission Operations Center, and this picture, he's actually teaching me how to take a selfie.
Don't you like the fact that you can still teach the mom of the New Horizons mission something? Yeah, very good. And on the right, what are these special treats that you have here?
So this is the globe is a globe that was created with the data from our spacecraft, and then I was honored that somebody.
There's a Lego.
Yeah,
there's an
a
Alice
Lego.
Bowman Lego.
Yeah. It's private issue. It didn't get enough votes. So if you're familiar with how Legos work, you can propose ideas for different sets of Legos, and then they have to get a whole certain amount of votes before they can be marketed. So this was proposed, but I didn't get enough votes.
But
I still
they
have
didn't
one.
contact us in the planetarium. We would have put you over. So we have, I don't want to go to it yet, we have a wonderful video because Brian created a song. You had an opportunity to hear it. So after questions, we will give you an opportunity to hear that song again with video from the New Horizon mission. But what I would like to do before we do that is to have a big warm round of applause for Alice Bowman, everyone.
Thank you.
And the chance for question and answer. If anybody has any questions, I understand that we have some roving people with microphones in the audience, and we're happy to take a couple of questions before we play that video and send you on your way throughout the evening or to look at a telescope or whatever else you might be doing. Now, it's a bit difficult to see out there, so maybe... All right, okay, good. Back there?
There's one here.
And we have one here, too. So we'll go back first and then up here.
What was the engine of the New Horizons made of?
Great question.
Like the engine.
So we used a rocket to launch the spacecraft, so you can think of that as kind of the first thing that we used to get the spacecraft out of the Earth's gravitational field. But then after that, we really don't have an engine on board the spacecraft. We have a nuclear power generator, so it provides power. And we have little teeny thrusters that actually enable us to point the spacecraft and change its path a little bit. But pretty much the rocket is the engine, the thing that gets us out of Earth's atmosphere and enough thrust to keep us going.
Good, now I can see. I see a hand here in the front. I think we've...
What was the day-to-day job of the people in the team between, say, Earth and then Jupiter and then Pluto? How many people were there?
So the question was, what was the day-to-day job of the people that were involved in the periods where we were waiting to get to Pluto? So between, after Jupiter gravity assist. So we were worried about that because, once you have a set of people that know the mission, you don't want to lose that expertise. But it looked like we were going to have to do that because there wasn't much to do except to, prepare that flyby sequence and take care of the spacecraft from Jupiter out to just before we got to Pluto. But what we did, instead of letting people go, we kept people on for a very small amount of time, so maybe 10 or 20%. So what that did is they kept their knowledge up about the spacecraft because they were continually involved, even at a small level. And they filled the rest of their time working on other missions. So very good question, yeah.
There's one here, and I see a bunch.
So the photos that were just taken in Pluto was close to a decade ago. Was that correct?
In 2015,
Did we recently get the photos from Pluto?
Yes, in 2015, and it took us until October of 2016 to get all the photos of Pluto down.
Okay. So
Yes.
if we had the technology that we had today in the rover that was taken a decade ago, what differences could we have seen with Pluto?
Okay, so I think I understand the question. If I get it wrong, please correct me. The spacecraft was built in the early 2000s, and we had to use, obviously, the technology that we had at the time. Launched in 2006. We didn't get to Pluto until 2015, so really a decade had passed with the technology that we used. And the question was, what if we built it today, what kind of improvement could we have seen? That's a good question. We were always improving our instrumentation, so perhaps we would have more fine resolution cameras on board.
But you were able to upgrade a lot from Earth as you went along, correct?
Yeah, so we could upgrade the
programs
software.
and software.
Yeah. It's a good question. I'm so used to working with what we have. It's really hard for me to answer that one. But I've just read in the last few days that there is an orbiter that is being studied. NASA just funded the SWIRI Southwest Institute to study orbiter mission back to Pluto. So I'm sure that's going to have the new stuff on it.
There's one there.
For the 5 moons that were displayed for Pluto, which one was the really super spinny fast one, and how fast does it spin? Like, that was the blue one, yeah.
The blue one, yeah. You know what? I'm not sure. I'd have to go on the website. You can go and see which one it is. They are some wacky moons. They really are, really, truly. And then Pluto and Charon are sort of locked. They're the ones that are staring at each other like this. So, yeah.
I see some kids back at the back.
How much computing power does the New Horizons probe have in compared to a computer nowadays?
Yeah. So the comparison I've heard was, are you guys familiar with the Xbox? Yeah. Okay. So the first one that came out, that's about the amount of computing power that the spacecraft has.
Okay, I see one here. I saw him before, here in the middle. I'm looking over. Raise your hand now if you want to be the next person while we give this person.
Hi, Alice. Thank you for the talk. Was there anything that you would have liked to have accomplished on the mission? Any data you may have liked to have gained on the mission that you weren't able to? I think you said you were 26 miles out from your point. Did you miss anything, do you think?
For that one, that measurement, no, because we were within that error box. But to me, it's a flyby mission, so we really only got to image one side with the high resolution. So when we came, you can probably find these. The last slide that I have is the website where you can go and see all the images that we took with the spacecraft. But Pluto has a 6.4-day rotation, and so we were only able to, kind of see one side of it. But when we were coming in, we were actually able to see take low-resolution pictures of the backside. And these were kind of like these swirly things kind of blurry, but I've always been intrigued. Well, what the heck are those swirly things? And I would really like to know. So that would be my answer to that question. The other side of Pluto. I'd like to see what's there.
Sort of like the dark side of the moon.
Yeah, that's true.
Do we have somebody here up front? Yeah.
How much assist did New Horizons get from Jupiter?
How much gravity assist? Okay, let's see. It's 21 kilometers per second. That's how much we sped up the spacecraft. So, 9,000 miles per, faster. So it shortened the transit time by 3 years.
Yeah.
And something I didn't mention in my show, the reason gravity assists work is because it stole that speed from Jupiter.
It did.
Very slightly slower. Really slightly slower.
Is Jupiter really bummed out about that?
Let's go ask.
Yeah, that's good. Let's have another mission. Alice, just while we're waiting, we're going to give that person a question. But when we were kids, you wanted to be an astronaut. How does being mom of New Horizons compare to your desire to be an astronaut?
No disrespect to the astronauts, but I really love my job, and I can do so much with a robotic spacecraft. I don't know. I'm very happy. I'm very happy with what I chose to do.
And your chance to explore, to boldly go.
Yeah.
Where no woman has ever gone before. Yeah. Sorry. Anybody else who has some? I'm just trying to call. Oh, yes, there's one there. I see you.
I was going
There's
to
one
stop
here too.
And at the
talking
back.
because I have a microphone. Could I ask, what was the budget you were given to achieve all of this?
So for the primary mission, so from the start where we started, we were funded 2002. So design, build, launch, get to Pluto, and bring the data down. So October 2016, it was $720 million, US dollars. So that is less than what it costs us to build a football stadium, American football stadium. I'm not doing too well with this.
There's a lot of numbers. There's a lot of numbers in this. All right. And a lot more interesting. All right, that was an editorial
There's
comment.
one
I
here.
apologize.
If New Horizons can turn, why can't you just get information from Voyager 1 or 2, find something you like, and study that?
So let me see. Repeat the question is if
I guess your question is, can't you use Voyager 1 or 2? Is that what you mean?
instead of New Horizons.
Like, why can't you just send someone to New Horizons, then use New Horizons?
So I think the question was, why didn't we send Voyager to Pluto instead of New Horizons? Perhaps, yeah, okay. So Voyagers, there's 2 spacecraft, and it's called the Grand Tour, and the planets were all kind of lined up so that these spacecraft could go and visit one and then kind of slingshot off and go and visit the other one, and they were in different directions. When one of the Voyagers got to Saturn, there was a choice that they could make. They could go on to explore Pluto, do a flyby of Pluto, or they could stay at Saturn. And when they got to Saturn, they just found that the moon Titan was just so intriguing that they decided to keep that Voyager spacecraft there to study the moon instead of going to Pluto. So that's why New Horizons went to Pluto, because the Voyager mission did not. They were studying a moon of Saturn. And the Voyagers didn't have, once you missed that opportunity, it would take so much more energy to turn the spacecraft to go see Pluto that they didn't have enough to go and visit. Did that help you? Yeah? Okay.
All right, we probably have a chance for a couple more. This is by the way, compliments to this audience. There's tons of great
They're
questions
great
here.
questions.
Awesome. There's someone back there. Yeah.
Are there any probes or machines on Pluto today, or are there any more coming?
Great question. How old are you?
9.
9. Okay, so maybe we have a future
we go.
mom back there. There are no rovers or man-made machines on Pluto. Our mission was the first to visit Pluto, a flyby mission. And this is how first visits to planets are done by NASA. First, you fly by the planet or the object and gain enough information so that you can send back an orbiter. And then perhaps after the orbiter, you send a lander of some sort, whether it be a rover or a quadcopter. And so, you know, the next mission to Pluto should be an orbiter where we can study more of it. So maybe we've got the future right there.
I see one there. Another hand right there in the middle of that row.
How much longer do you have with the nuclear fuel?
Yeah, so how much longer do we have with the nuclear fuel? It's plutonium, and plutonium has a half-life of, I think, about 89 years. And when we started the mission, we had about 240 watts of power. When we got to Pluto, we had about 200. Ultima Thule, about 190. And when we get to the mid-2030s, we believe that we won't have enough to turn around, to turn on the transmitter and send data to Earth. So we believe that the New Horizons mission can return scientific data up until that point, so mid-2030s.
All right. I think we will probably wrap it there unless I'm going to let you be the lucky last. I saw your hand. I hate to leave a question unanswered. And then when you've gotten an opportunity to ask your question, we'll play a cool video as you leave. Go right ahead.
What do you do now?
Because
you've been, stressed for a lot of years.
Yeah, stressed for a lot of years. Stressed and amazed. So, I mean, they kind of balance each other out. Probably more of the amazed part, the positive part. But I still am mom for the New Horizons mission. We're still bringing down data from the Ultima Thule encounter that we had this past January. It actually is going to take us quite a while to get it down. As the spacecraft moves further from Earth, those data rates decrease. And so it just takes longer to bring that data down. So I'll continue with that mission. I also manage the group that does the other spacecraft operations for the Applied Physics Lab. So we have stereo mission, we have time mission, we have a new mission coming up called Dragonfly, which is to go to Titan and study Titan, the moon of Saturn, that we talked about, that Voyager was so intrigued with. And we're going to use, instead of a rover, we're going to use a quadcopter. So we'll send the spacecraft out to Saturn. It's going to take quite a while to get there. The planned launch is in 2026. And I think we're supposed to get there in 2034. So again, patience is the name of the game here with the space exploration. And then this quadcopter will separate from the spacecraft and come down onto Titan and do a little bit of surveying around to make sure that that's where they want to land. It'll land and take some measurements, probably on about 3 months or so, and then it will go off to its next destination. So it'll be able to study a lot of different parts of Titan. It won't be so constrained as a rover. And because we can do this because Titan has an atmosphere. So you can't really fly anything if you don't have an atmosphere. So this is quite intriguing. We're kind of excited about that. So yeah, there's a lot of things.
So from the days when we watched Star Trek, you're still just as excited about space
Oh my
as you were
gosh,
back
yes,
then?
yes. So excited. There's so much to learn. So much.
All right, ladies and gentlemen, we're going to leave it there. And as we wrap up, I will give you an opportunity to watch a little bit more of New Horizons to the song. Well, tell us about the song.
Oh yeah, our PI Alan Stern gave Brian May this challenge, and he said, you know, you should write a song for us. You know, all the things that we have done and accomplished. And Brian said, well, I don't know about that. He was kind of lukewarm. He says it's really hard to find something that rhymes with Ultima Thule.
And on that note, let's have a listen, and good night, everyone, and thank you so